Well, time to get rolling here on chapter 8. We switched gears a little bit from 7b, which was solve. Yeah, we're stepping away from that. We're moving back in chapter 8 towards kind of working with some more geometry type of problems where we're solving angles, distances, right? Lengths of line segments on problems that can be related to triangles. But I'll give you kind of the overview on 8a, right? Again, 8's our final chapter. We're going to split it into two parts, 8a and 8b. What we're focused on in 8a is to make the jump to doing some of those kinds of geometry problems with triangles with like using non-right triangles. Okay, we're not going to make that jump until section 1. You see I've got this little kind of refresher section called 8.0. So what I want to do here is to refresh how we looked at like these kind of problems if we could relate it back to a right triangle. 8.1 and 8.2 will make the jump and look at problems where, okay, we're still doing the same kind of stuff, but it involves a non-right triangle. Okay, that's where we're headed in the next couple of weeks. So if you have a right triangle and you're solving for a side length, you got a couple different options here. You can go with the Pythagorean theorem. It's always an option, right? The only limiting factor is if you wanted to use it to find a side length, you have to know 2. Okay? I don't know if I've used the acronym SOHCAHTOA. You have probably heard it before at some point. That's just to remember the 3 basic trig functions that we use. Okay, SOHCAHTOA is like using an equation with a trig function. Okay, this would come up if you know an angle, and then you only need to know one side, right? But if you're looking for a side length, you've got those 2 options. Okay. If you're looking for an angle, right, you can use the fact that the 3 angles in a triangle have to add up to 180. You have to know 2 of the 3, and you can use it to get the third. Right, the other option is you can use another equation involving SOHCAHTOA. You just need to use the inverse if you want to go back and to get an angle. By the way, when we're doing these kind of triangle problems, we always stay in degree form. Okay? A couple other kind of last minute things here. If you're getting angles inside, rounding to the nearest 10th is just fine. But if you're rounding a trig function, because this can really have a bigger impact on your answer in terms of accuracy, round it to 4 decimal places. Okay, that'll give us the accuracy that we need. Down below, you've got a little diagram with just a little terminology right here. Okay. Angle of depression, if you see that term, would be referring to something like that. Angle of elevation is there. These 2 sides right here would assume to be parallel. And the big thing with those 2 angles, the measure of angle 1 would be the same as the measure of angle 2, right? In other words, for any like given word problem, the angle of elevation or depression it ends up being the same angle. All right, enough of that. Let's do some solving. Okay. Again, each of these sketches that I'm drawing here, right triangles. Here's DEF. I'm going to call this angle theta, that one alpha. Okay. This side is 6. This side is 20. In terms of a variable name, let's call this A, call this B, and we'll call that C. Okay? I don't believe I know anything else in the problem, and that's what it gave me. Basically 2 sides. DE is 6, DF is 20. All right, if I want to get b, I could go 6 squared plus b squared is 20 squared. Do a little solving. Let's see here, subtract 36, and you get that b squared is 364. Square root, should get that b is about 19.1. Takes care of my side length. That was missing. Now I've got two angles. Okay, I'm gonna go get, I'll get theta first. With having all three sides, there's a variety of different ways I could set this up. I'm just gonna go with cosine of theta is 6 over 20. We saw this operation quite a bit when we were solving. We just do an inverse. That would go into our calculator, and we would get 72.5 degrees. Okay? If we're working within a triangle, okay, all of our angles need to be less than 90 degrees. So just right here, I don't think you would worry about this, but just so we're clear on the difference. When we were solving in 7b, right, we were always like, hey, we do that inverse, we should get two solutions, right? Well, you're safe if you're working in a triangle. The only solution you want is the one the calculator would give you. Like for cosine, the second rule is 360 minus your first answer. That number is going to be over 90 degrees, and that can't be an angle inside of a triangle. So we don't care, right? We don't need to apply that rule ever in Chapter 8, right? We'll just take the one answer that the calculator gives us, okay? And it's always going to give us one that's less than 90, okay? A lot of different ways we could get alpha. I'm just going to say sine alpha is 20 over 6. Take that inverse, 17.5. There you go. Okay. Now, if you're wondering for maybe even a faster way, you could have done 90 minus 72.5. That's a valid way to do it, right? You had two angles, right? Because I just basically took out the right angle. You got the other two left over. 90 minus the first one you found to get the second. That would work too. All right, again, let's start with a nice diagram. I don't really draw them to scale, and I always tend to kind of draw my diagrams the same way. As long as it's just a nice basic right triangle. Now, it does say right here that C has to be the right angle, so I need to do that. So here's A, here's B. A is 35. You know what? Like right off the bat, just from that whole deal that they have to add up to 180 degrees, I'm just going to enter that B is 55. I know that right away, and it wants me to solve this triangle, so I'm going to put that on there. And then it tells us the hypotenuse is 14. We'll call this little b. We'll call that little a. Okay? Now, I didn't really stress this much in the first slide. If you're looking at all this and you're like, Mr. P, I know how to do this because early on in the semester, we did this a lot, right? Yes, right? This is 8.0. We're calling it a refresher, right? So this is just, we've seen right triangle problems. It's a review, right? We're kind of bringing them back to kind of set us in this new direction for where we want to go in 8.1 and 8.2, which will have stuff that's new. Hopefully earlier I made that clear. Maybe I didn't. All right, I think I'll start, I don't know, let's go right. I'd like to get this one right here. Variety of different ways, once again, you could set this up. I'm going to say this. I'm going to say cosine of 35 is adjacent over hypotenuse, or b over 14. By the way, to get all these answers, these are all calculator based. You're not typically in this kind of stuff going to end up going to the unit circle. Lots of decimal approximations. Not a huge focus in this kind of stuff to get exact answers. Now I'm going for A. Let's see, let's just stick. If I stick with 35 degrees, I can now go opposite over hypotenuse and say sine of 35 is B over 14. And then what you type into the calculator would be 14 times the sine of 35. That's going to give you B. Whoops. Back up. Already found B. Not interested in B anymore. I mean, not like disinterested. I just know that it's 11.5. What I want is A. At the moment, A is still unknown. 14 sine 35 from your calculator should give you right around 8. Right around 8. Find the measures of the acute angles, right? Acute meaning less than 90. So here's what we have. This side's 3. This side is 4. This side is 5. 3, 4, 5. We'll call this angle A. We'll call this angle B. Essentially, I'm just interested in finding those two angles. Okay, that's all I'm after. I'll start with A. Let's see here. The sine, I'm going to go sine of A is 3/5. So then if I want to get angle A itself, I just need to do, on my calculator, inverse sine of 3/5, which should give you 36.9 degrees. Now let's go find B. You know what? Let's stick, I'm going to switch over with cosine. Right, but now I'm going adjacent over hypotenuse. So then I just need to do inverse cosine of 3/5. And we'll get about 53.1. This is another case if you were looking at this and like, hey, couldn't I just go 90 minus 36.9? That would work too, okay? I've had kind of a preference towards trig functions today. I don't really know why. I just have. There's been cases where I could go, not every case, but where I could just use the fact that the triangles add up to 180, and I haven't. I've done another inverse trig function to get an angle. It's just been my preference today. Don't know why. All right, a couple word problems to kind of wrap up our review of a right triangle refresher, okay? Plane takes off at an angle of 22 degrees and travels for 110,000 feet. That's got to be a right angle. What is the height of the airplane? Okay. Now if I'm going from this angle, I like opposite and hypotenuse, so I would say sine of 22 equals my unknown side over 110,000, right? Multiply both sides by 110,000. And we get that. I'm hoping you see there that the math involved is nothing new. That should be 206.7, by the way. And here I actually have some units because our problem has a context to it. 41,206.7. All we did is add a word problem to it. Again, it's really important to always remind ourselves when we see a word problem, there's nothing new in terms of the math involved, right? That's the idea, is when we don't have a context to practice the skill, then we actually go to a word problem, and it's just a matter of taking the same skill and seeing how it applies to that information. Let's do one more. All right, so we're climbing up a mountain here, right? I'm going to draw it like this, because this is going to come back in the problem, that we're already at an elevation of 11,200 feet, okay? And we're standing right here, and we're going to go on an ascent to the ridge. The ridge is right up here. We're climbing at an angle of 29.4 degrees. And it tells us the horizontal distance right here is 6,315 feet. Okay? We want the altitude of the ridge, which is, on my diagram, this. But keep in mind, this part right here, I don't really care about it until the very end, because I just need to tag on 11,200. What I need is right here, okay? I start at 11,200. How much did I go up, right? Because once I get that, I can tag it on to 11,200, and I've got how high the ridge is, okay? I need to use that side, which is opposite. This other side right here, I know. Opposite and adjacent is tangent. So I go tangent of 24.9 equals x over 63.15. Multiply both sides by 6,315. So in our hike, we gain 3,558.3 feet to get our final answer. Excuse me, 0.3. Excuse me again. Sorry about that. $14,758.3 feet would be the height of the ridge. Now, I might want to double check this problem. It says we're in Utah. Pretty sure we're not in Utah because, one, I think the highest point in the contiguous 48 states is Mount Whitney at 14.5. So we can't actually be at 14.7. And I don't think Utah has any peaks over 14,000 feet. So maybe look into that a little bit. Not sure certainly that math is possible on our hike. We might have been in Alaska. Okay, just saying. I'm not positive we were in Utah. So, but yeah, the only additional kind of new piece on that one is just to add that component of 11,200 in your diagram and then add it to your final answer.